Hello, everyone, and welcome to another wonderful day of physical chemistry. So, last time we were talking about a particle in a box. And when we meant particle in a box, what we meant was particle in an infinitely deep box. Now, it turns out that most of the time, if a particle is trapped in a potential, it ain't exactly infinitely deep. Now, enough times it's deep enough that infinite is a good approximation, and this can actually be the case in particles trapped in certain molecular structures. However, a lot of times it can actually escape its confines. So it's trapped in what we call a finite box. So this means that our potentials are going to not be infinitely high, and so we need to describe essentially a system with a barrier of height V. So V is going to be essentially the potential energy barrier to escape the well. Now, one of the crucial parts about dealing with this type of square well is that these walls aren't also infinitely deep. There's some place with a zero potential outside the well. So this may be jumping from one molecule to another, which is a classic version of a finite potential well, or it could be essentially dropping from one material to another. And we'll talk about several applications as we go on. And so we also are going to describe the system with a well width of W. Now, this leads us into several important cases. So, first of which is actually kind of the classical scenario where where my particle has an energy that's greater than essentially the potential energy barrier. So, this means that my particle has a lot more energy than the well is deep. So, in this case, we'd expect the particle to be found inside the well and outside the well, with a slightly higher probability of being found inside the well than out because it doesn't like going through a high potential, but it will. The probability outside is going to definitely be non-zero. And this is exactly what I'd expect in a classical scenario. Now, the interesting case happens when the energy of the particle is less than the barrier of the wall. And classically, what this would tell me is that the particle is likely not going to be found, will only be found inside the box. It doesn't have enough energy to get over the barrier. Quantum mechanically, not exactly the case. Quantum mechanically, it turns out that there's a small chance the particle can be found outside the wall, inside the box. Most of the particle will be found inside the box. Slight chance it'll be found outside the box. And even there's a decent chance that it'll be found inside the wall itself. So the way I like thinking about it is classically, I'd have water in a in a glass cup. The water is going to be inside the cup if the depth of the water is lower than the depth of the cup. If the water overflows, has more energy, it escapes. Enough said. However, it turns out that a quantum particle is a little bit more like running up against the levee. So most of the water will be found outside the levee. It's not going to be able to get through. However, as anyone can tell you, water does actually seep into the soil of the levee itself. And if the levee isn't very tall, I'm going to find more water sneaking through the levee. The other important feature, this essentially is what we call tunneling, where there's a slight chance to find our particle, just like water, seeping into the levee wall and through the other side. And anyone who's lived in a floodplain will tell you nothing's quite as bad as a leaky levee. And that's really what happens with quantum mechanical particles. However, it turns out we can actually extend this analogy a little bit further. Because it turns out that wall height isn't everything. Turns out wall width is also going to be important. So again, just like a levee, the higher the levee and the wider the levee, the less likely water will essentially seep through it. And this is the same thing with tunneling. If I have a very high wall, it ain't going to get through. If I have a very thick wall, it ain't gonna get through. So part of trying to keep a particle trapped is trying to balance this idea of width and height. There's going to be a certain portion that'll essentially drop the amount tunneling down to zero. So when people are talking about electron tunneling or particle tunneling or quantum tunneling, this is really what they're referring to. However, this also has some fun implications. First of all, because not all walls are essentially going to be infinitely high or infinitely thick, what it turns out that this means is there's going to be a slight probability of finding the particle in the wall or outside of it. So what this effectively does is it widens the size of the box our particle is caught into. And as a result, it means that our wave function and thus the probability density are also going to essentially be a little bit more spread out than we typically would expect. So this means a little bit lower probability of finding the particle inside the box, as well as a much higher variance in where the particle is located, much more likely to be caught out here in the edges than in the center, than when compared to an infinitely deep box. Now, the other problem we have to run into is that this also really complicates our wave function. Because remember, one of the big things we used to build our wave function was the fact that we set the value of the wave function to 0 at one wall and 0 at the other wall. Whereas you notice here, in a real potential well, a real finite well, that ain't exactly the case. And that's really going to complicate our wave function. That said, we can still really kind of describe our wave function the same way we always did. There's always going to be a certain degree of the particle moving forward, certain degree of the particle moving back. But the real problem comes with this k, because remember, this is the portion that we use that we established by setting those boundary conditions. Here, all we have is, if I know the energy of the particle, I can still relate that to my prefactor in the exponential term. Because again, the energy gives me the momentum. The momentum is really kind of what I'm tracking with these exponential terms. However, the problem is that while we still have discrete energy levels, it's much harder to try and guess at what those energy levels are. And so it's worth noting that there are a set of equations to do it, but congratulations, we've just left the field of chemistry and moved on to quantum mechanics. So if you're really interested with that, go ahead and pound on some doors over in the physics department. This is kind of where I've hit the level of quantum mechanics I expect most of you to know. However, it is worth noting that as a well does become deeper, essentially that potential wall gets higher and higher, it's going to become much easier for the well to trap a particle. Because you can imagine a very shallow well can maybe have one energy level. As it gets higher, I can maybe expect 2 or 3. We eventually get to the point where the energy of the part of the next state is essentially outside the well. And really what happens is we can kind of accommodate one more state than the well allows. So there's going to be one state where the energy is slightly higher than the barrier. And you can kind of think of this as if you fill a glass cup, you can fill the water level just a little bit higher than the edge of the cup before it all spills out. And it's kind of the same thing with a finite well. However, one of the things that is worth noting is if I have a heavier object and a longer wavelength, it's going to be much more likely to be trapped in the well. So again, longer wavelength, lower energy, less likely to bleed out, as well as the longer the well itself, the more likely I am to be trapped in the system as well. So again, one of the big things to make note of is that it is actually possible to determine exactly how many states you can trap in a finite well. And not too surprisingly, the key features here are the mass of the particle, heavier particle, less likely to tunnel out, less likely to go over the edges. The depth of the well, a deep well will essentially keep a particle well trapped. And then the last major portion, the size of the well. So a wide, shallow well can keep a particle fairly well trapped, or um, a narrow, deep well can also keep a particle well trapped. And again, you can kind of think of this in the same lines of how much water can I hide in a hole. Either you can put all your efforts to making a big hole that isn't very deep, or vice versa. And again, you can. This does give us a formula to figure out how many states can be trapped in there. So essentially, what you're going to be looking for is finding the energy value from this expression. And then you're going to be finding the integer value that's one lower. So you'll take this value and then find the nearest integer. And that's going to be more or less how many states you can keep trapped in. So that kind of brings us the idea of a finite well. But it turns out that one of the really important features of tunneling is less how well I keep a particle trapped in. Don't get me wrong, that's still fairly important because that's a lot of molecular systems. But it's also important to figure out how likely a particle is to jump from one state to another, because down that road leads us to tunneling electron microscopy. And who doesn't love some good microscopy? Until then, take care.